Hi there. So for this video, we're going to be working on a rotation problem. So for this problem, the angular position of a point on a rotating wheel is given by theta equals 2 plus 4t squared plus 2 times t to the third power, where theta is in radians and t is in seconds. So the first thing we want to do is to draw a diagram of the problem. So as you can see, I've already drawn our wheel right here. So now let's go ahead and draw or superimpose an x and y axis on top of the wheel. So here we have our y axis, and here we have our x-axis. Okay, so we have y and this is x. So the wheel is going to be rotating either counterclockwise or clockwise, parallel to the page. Right, that's our plane that the wheel is going to be rotating parallel to. So now let's go ahead and draw a point on top of our wheel. So let's call this point right here point P. And now let's go ahead and draw a line connecting point P to the center of the wheel. And let's call this point the origin, or O for short. So let's go ahead and draw a line. I'll draw it in red. So this is going to be the line that connects point P to the origin. And so this line is going to make an angle with the x-axis that we call theta. Right, that's going to be the measurement of the angle between this line right here and the x-axis. So as the wheel rotates, the point also rotates as well, and therefore this angle changes with respect to time. Therefore we have a relationship between the angle and the time, and we describe this relationship as the function theta equals 2 plus 4t squared plus 2 times t to the third power. So let's go ahead and write that function down. 4t squared plus 2t to the third power. Okay, so at 0 seconds, its angular position is going to be given by theta equals 2 plus 4 0 seconds squared plus 2 0 seconds to the third power. Right, this gives us the position of this point at 0 seconds with respect to the positive x-axis. So solving for theta gives us 2 plus 0 seconds squared is just 0, plus 4 is 0, plus 0 seconds to the third power, which is just 0, times 2 gives us 0, so theta equals 2. And as the problem mentions, theta is going to be in radians, so this is going to be theta equals 2 radians, right? So at time equals 0, its position is going to be at 2 radians. This is its initial position with respect to the positive x-axis. This is where the point starts on the wheel. So so if we draw a unit circle, right? If we imagine this wheel as a unit circle, so the positive x-axis, which is in this direction, it starts at 0, right? The positive y-axis has a angle of pi over 2 radians. The negative x-axis has an angle of pi radians. The negative y-axis has an angle of 3 over 2 pi radians. And then as we rotate all the way back to the positive x-axis, this gives us an angle of 2 pi radians. So pi is about 3.4. So from here, from the positive x-axis to the negative y-axis, to the negative x-axis, that's going to be about 3.14 radians. So about half of that is going to be 1.57 radians. So the point is going to start somewhere in this quadrant, this second quadrant. So point P is going to be most likely somewhere here. So now we want to find its angular velocity at this instant, time equals 0. So this is going to be its initial angular velocity, right? The velocity that the point starts out with, right? This is how fast the wheel starts to spin. So essentially, since we want to find its angular velocity at a certain instant, t equals 0 seconds, we have to use the formula for instantaneous angular velocity. So the formula for this is, we say that angular velocity is going to be equal to omega equals the derivative of theta with respect to time. So this is going to be the derivative of its angular position, right? The instantaneous rate of change of its position with respect to time. So taking the derivative of our angular position formula will give us its instantaneous angular velocity. So d theta over dt is going to be equal to the derivative of 2 plus 4.0 t squared plus 2 times t to the third power. So all we do is take this formula and plug it in to theta, because we know that theta equals this formula to the right of the equal sign. So when taking the derivative of a polynomial, we can break it up into smaller derivatives, right? So we can break up this derivative into smaller components, right? So we can say that this derivative is equal to the derivative of 2 plus the derivative of 4t squared plus the derivative of 2t to the third power, right? So if we take the derivative of each individual piece and add them together, it should give us the formula for the instantaneous angular velocity. So just a quick review of derivatives. Let's say we have the term x to the n power. To find its derivative, all we do is bring this n down in front of the term and then subtract 1 from the exponent. So this is going to be n times x to the n minus 1 power. And this applies to all terms in this form, x to the n power, some variable to the n power, to some number as a power. So in this case, for the first term, 2, it may not look like 2 has a variable in front of it, but it actually does. So we can actually think of 2 as 2 times x to the 0 power. Right, and this is because anything to the 0 power is just 1, and then 1 times anything is itself. So 2 to the x to the 0 power is just going to give us 2 in the end. So if we were to subtract 1 from the exponent, actually let me rephrase that. If we were to bring down the 0 and then subtract 1 from the exponent, which is 0, it would just give us 0 times 2 to the x to the negative 1 power. So multiplying 0 by the whole thing will just give us 0 in the end. So this is actually going to be equal to 0. The derivative of 2 is going to be 0. In fact, the derivative of any constant will equal 0, right? Because they all have this form. So now going to the derivative of 4 times t squared, right? All we do is bring down the 2 and then subtract 1 from the 2. So that gives us 2 times 4, which is 8. Times t to the 2 minus 1 power, and that's going to be 8t, right? So this is going to be 8t, and then for this derivative we have 2 times t to the 3rd power. So once again we bring down this 3 and then subtract 1 from the 3. That gives us 6t squared. So this is going to be the formula for the instantaneous angular velocity, right? So in this case, to find the instantaneous angular velocity at a certain time, all we have to do is plug in the time that we want to evaluate this function at. So in this case, we want to find its velocity at time equals 0. So in this case, we just plug in 0, right? So this cancels out. So we have 8 times 0 plus 6 times 0 to the 3rd power. And once again, 8 times 0 is just 0. And then 0 to the 3rd power is 0 times 6, 0. So this is just 0. And the units that we use for angular velocity is going to be radians per second. So what this tells us is at time equals 0, its speed, its angular velocity is going to be 0, right? And this makes sense because at time equals 0, the wheel is going to be stationary. It's not going to be moving at all. So for part C, we want to find the angular velocity at 4 seconds. So once again, we just repeat the same process we did for part B. We just take our formula, which is omega equals 8t plus 6t squared. And then wherever we see a t, we just plug in 4 seconds, right? So in this case, we have 8 times 4 plus 6 times 4 squared, right? In this case, 8 times 4 is 32, and then 4 squared is 16. 16 times 6, that's going to be 15 times 6, which is 90, and then 1 times 6, which is 96. So 90 plus 6 is going to be 96, and then this whole thing is equal to 128. So our angular velocity at 4 seconds, in this case, is going to be 128 radians per second. So every second it travels 128 radians, right? So okay, so for part D, we want to calculate its angular acceleration at 2 seconds. So what this basically means is that we want to find the instantaneous rate of change of its angular velocity at a certain time, in this case 2 seconds, right? Or in other words, it's instantaneous angular acceleration. So at what rate is the velocity changing with respect to time at 2 seconds? Right, 2 seconds after it starts to spin. So therefore we simply take the derivative of its angular velocity, omega. So our angular acceleration is going to be equal to the derivative of omega with respect to time, right? And so we just take the derivative of our angular acceleration equation, which would be, our angular velocity equation, which would be right here. So in this case, we have the derivative of 8t plus 6t squared. So essentially, we can just break up this derivative again into smaller components, right? If this helps you solve it easier, right? So in this case, we have 8t. So 8t is actually going to be the derivative of 8t to the first power, right? Because anything to the first power is itself. So t to the first power is simply t, and then 8 times t is going to be 8t. So in this case, we can bring down this 1 in front of the 8, and then subtract 1 from our exponent, which is 1. So 1 times 8 is 8, and then 1 minus 1 is just 0. And as we said before, anything to the 0 power is going to be 1, right? So this is going to be equal to 1 times 8 times t to the 0 power, which is just 1, or just 8. And then we're going to add the derivative of 6t squared. So the derivative of 6t is going to be, so we bring down the 2. 2 times 6 is 12, and then we subtract 1 from the 2. That's going to give us simply 1, right? So that's going to be 12t, right? So this is going to be our angular acceleration formula. So now in this case, to find the angular acceleration at 2 seconds, right? At t equals 2 seconds, we just plug in 2 seconds. So in this case, we have 8 plus 12 times 2, and this is equal to 8 plus 24, which is equal to 32. And the units for angular acceleration is radians per second squared. So just like the units for linear acceleration, except in this case we're using radians instead of meters. So for part E, because the angular acceleration depends on the time, t is not constant. Or in this case, its acceleration is not constant. Because its acceleration is not the same at all times, right? Because there's a variable here, right? Because there's a variable in the equation, the acceleration is going to vary with time, right? It varies based on what time we have. If we imagine that t equals 1 second, this would be 8 plus 12 times 1, which would be 8 plus 12, which equals 20 radians per second. And in this case, right, because we have a varying acceleration, it won't be constant. Remember, acceleration is a derivative, right? And a derivative is simply a slope, right? It's a rate of change. So if it were constant, the slope of its curve would be sort of a flat line, something that looks like this, right? Here's our acceleration and here's time, right? If it was constant, it would have a slope of a flat line as its slope. Because the acceleration at any point in time is going to be the same, right? So, but however, in this case, since our acceleration formula has a variable in it, right? It varies. So its graph is going to kind of look like this, right? Here's our t-axis, here's our a-axis, and our formula is going to be 8 plus 12t. So our y-axis is going to be where t equals 0. So there's going to be an 8 right here, and then it's going to have a linear graph that has a slope of 12. So our graph is going to kind of look like that. And so as time goes on, its acceleration, its output is going to change accordingly as time goes on. So for that reason, its acceleration isn't going to be inconstant. It's not going to be constant. So that's going to do it for this video. Thank you for watching.